Welcome back, guys. As you can see today, I got more potatoes. We got 246 potatoes. We're going to be ripping some high voltage here. I've connected them all positive copper electrode from one side to the negative zinc electrode to the other side, all of them in series, so the voltage should add up. In theory, you should be ripping about 1 volt from each potato. In reality, it's going to be a bit less. I've checked each of these guys. They're about like 0.9, 0.8 volts. And I've connected the ends over here, and I got my voltmeter. So we're gonna put this red bad boy to the copper of the first potato, and we're gonna put this black one on the zinc of the last one, which is right here. And you can see we're ripping 5 volts. This is crazy. You can absolutely jumpstart a car with this. Let's check the current. We got about 150 microamps. It keeps dropping. I'm not too sure what the reason is, but the voltage is what we care about. Looks like the voltage dropped a bit once I went to check the current. So we're gonna test it out here today and see if we can light up an LED. I got over here 4 different colored LEDs. And what you may notice is that an LED has 1 long leg and 1 short leg. The long leg always has to be connected to the positive side, which is going to be, in our case, the copper. You cannot run the LED with reversed terminals. It acts kind of like a one-way current limiter. And check it out. Boom, we got a green LED to light up. Not too bad, right? Looks pretty good. Maybe it's getting dimmer as we go on, but let's check out the other colors because I know that some of these guys require a bit more energy. Let's check the blue one here. Blue LED, ripping, looking absolutely amazing. I like the blue one. I think the blue one takes the most energy to light up. Let's check out the yellow one over here. Ooh, yellow one looks the most dim. I don't know if you guys can see this on the camera. And let's check the red one. Some Spidey physics red. Red one also lights up pretty good. Nice. So the theory has been proven, guys. If you're ever in need of a quick jump start for your car, or you need to charge your phone out in nature, hook up some copper wire and zinc bolts to a potato, run 6 or 7 of them. You could probably get like 100 of these bad boys and get 100 volts. Try it out at home. Now let's go check out why this works and some of the theory behind it.
What to do, squad? This is the theory part of the video. We're going to see what the hell's going on inside the potato and with these copper and zinc electrodes to actually get us a voltage. So I got 3 slides here for you today. We're going to start off with the important parts of the battery. You need to have an anode, a cathode, and an electrolyte for any battery you're talking about. In our scenario, we got a zinc electrode, which is going to be the anode, a copper electrode, which is going to be the cathode, and the potato and the juices and stuff inside the potato is going to act as the electrolyte. Every battery needs something like this. In our scenario, these are the things we're going to use. In different batteries, the electrodes, or the cathode and anode, and the electrolyte are going to be different, all right? In our example, right, we got these guys, and an important thing that you need to consider here is oxidation and reduction reactions. So this specific scenario, we got oxidation happening at the anode side, and oxidation is a loss of electrons. We're going to see a little bit more how to memorize this in the following slide. You can see this little half reaction going on here. We got solid zinc. This is the elemental symbol for zinc, Z, capital Z, lowercase n. This is going into, or turning into, zinc 2+, which is a zinc ion, plus 2 electrons. Everything here is balanced, and it is a loss of electrons because zinc here is going into something that is losing electrons. On the cathode side, we have reduction, which is a gain of electrons. We have a copper ion, this Cu2+, and if you add 2 electrons to it, right, a gain of electrons, you transform that to regular copper. Here we got a little diagram of what is happening in our potato battery. We got the little LED here that we're lighting up, and you can see the flow of electrons going through here, and some little symbols and reactions and stuff happening here. Here's a more simplified version of what the battery looks like, with some other stuff here, some anion flow, basically the same picture. So the main important stuff you need to consider here is the anode, the cathode, and the oxidation and reduction reactions. How do you remember this? We got a couple of nice mnemonic memory techniques and some images that can help you. So for reduction, you can remember red cat. Red stands for reduction, cat stands for cathode. And you can see here, this little red cat is going to help you remember that reduction goes with the cathode. For oxidation, you can remember an-ox. An stands for anode, ox stands for oxidation, and you can see this here goes for the zinc, which is going to be our anode. Another thing that you can use to remember is this oil rig. Oil rig stands for oxidation is loss of electrons and reduction is gain of electrons. So whenever you have an oxidation reaction happening at the anode, that is a loss of electrons because of oil. And whenever you have reduction happening at the cathode, that is a gain of electrons because of this rig over here. So these three pictures will help you remember what's going on in our specific setup. How do you know that the zinc is actually the anode and the copper is the cathode? We don't know this yet. Zinc is a more reactive material, so it is more willing to give away some of its electrons, and copper here likes to accept the electrons. So you can think of zinc as the more reactive metal, which makes it the anode because anodes like to oxidize. Sounds good? Now let's move on to the last slide here. What we're going to talk about here is how you can determine what voltage you get from your battery. So what's happening here is some standard reactions. You've seen these little half reactions here. The reduction of the copper, reduction is gain, remember? So copper here, a copper ion is gaining some electrons and it's turning into copper, regular solid copper. And you can see here this E subscript cathode with the little symbol on top is the electrode potential. Right, you can see that right here, boom, in volts. So you can see for this reaction in red, the reduction of copper, you have 0.34 volts. This is the voltage that we get from a reduction reaction of copper. Similarly for the zinc, zinc is oxidation, right, because it is on the anode side, and you can see here solid zinc converts into a zinc ion and 2 electrons. So the zinc is losing electrons. The electrons on the other side of the equation here, so this zinc here has to lose some of the electrons. And because of that reaction happening, this zinc oxidation reaction, we get an electrode potential at the anode side of negative 0.76 volts. Very interesting. Overall here, this reaction that is taking a set of copper ions and zinc and transforming it into the oxidized version of the zinc and the reduced version of the copper. You can combine the electrode potentials for each of those, which in our case is going to be 0.34, which is coming from this reduction reaction of the copper, 0.34, and you add to that 0.76. You're adding it, even though you're supposed to take a little negative sign here, the negatives cancel out. So you basically add these two electrode potentials. Again, what's happening is the reduction of the copper and the oxidation of the zinc. You combine these two and you get 1.1 volts. So 1.1 volts is the highest possible potential we could get from this kind of setup here, stabbing our potato with a zinc metal bolt and with a copper metal wire. This is in theory, right? In reality, we're going to have some kind of imperfect conditions happening. The temperature of the room, the concentration of the electrolytes, impurities inside the zinc and the copper. So we're not going to get exactly 1.1 volts. Check out my previous video. I measured the voltage on all of the different fruits and vegetables, and we saw they were all a little bit less than 1 volt. There was maybe like 0.97 was the highest voltage that we got. So why is this important? Well, the electrode potentials here depend on the chemical reaction happening. In our case, we have some copper reduction and some zinc oxidation. So you can see that the potato is actually getting voltage based on the materials that you're stabbing it in. The potato doesn't really matter. This is why we got the same kind of voltage for all the different fruits that I measured in my first video. We measured an apple, a lemon, a potato, and I think it was an orange, and they all gave us roughly around the same voltage. Why is this the case? Because we always use the same materials. We always use the zinc bolt. We always use the copper wire. So the reactions happening here are always going to be the same. One important thing I need to mention is how you calculate these electrode potentials. Where are we getting this number for 0.34 and this negative 0.76? Well, there's some very nice scientists or very nice at-home experimentalists that have conducted this reaction here. They've measured it very carefully. They've reduced this copper and measured how much voltage it is emitting. And at standard conditions basically means standard pressure, temperature, electrolyte concentration, you get 0.34. If that changes, if the room temperature changes, increases, decreases, if the concentration of the electrolyte increases, decreases, if the materials are a little impure, you can imagine if there's impurities in this zinc or in this copper, it's made out of different things, you're going to have other reactions happening here inside this copper and this zinc. So you're not going to get exactly this. So this is standard potentials that you get from this reaction. I don't know exactly how they're calculated. I'm not a chemist. I just know there's some very smart people that have conducted this in very controlled environments, and they've found out that the reduction of copper, specifically copper ions into copper solid, gives you 0.3 volts from the cathode side here. And the oxidation of zinc gives you negative 0.76. Why is this one positive? Why is this one negative? I think this is just standard. If you flip this reaction here and you actually check on the reduction of zinc ions to zinc solid, you can flip this negative sign and make it a positive sign. It's going to be 0.76. Pretty much the same thing. It just depends which reaction you're looking at. In this case, we're looking at reduction at the cathode side, reduction of copper, and oxidation of zinc. If you flip them, you're going to get the opposite sign, but the same magnitude of the voltage. I think standardly, in most experiments, people really care about the reduction. So whenever you search up electrode potentials, normally you're going to look at the reduction of some kind of material, not the oxidation, but it doesn't really matter. So what's the important thing that we learned here? Each material has a chemical reaction it is undergoing, specifically redox reactions in batteries. This is the most important chemical reaction. Redox reactions are basically moving of electrons. You can see the electrons here are coming from the copper side. Copper is gaining electrons and the zinc is losing electrons. So electrons are moving from the zinc, as you can see here, these little E negatives are the electrons. They're flowing from the negative zinc side to the positive copper side. This is creating a current, but also from the electrode potentials, which are calculated from some standard conditions in a laboratory somewhere. You can find out the potential, which is going to be 1.1 volts in a perfect scenario. Awesome. Now you guys know that the electrolyte doesn't really matter. Maybe it does, maybe it doesn't. Very, very minute. The important thing is the reactions happening at the cathode and anode, or at the electrodes of the battery. If you change the material, so we change copper to something like aluminum, or we change zinc to something like iron, I don't know, you're going to get different electrode potentials and your battery is going to create a different voltage. You can use this with a little bit of a cheat sheet, search up online electrode potentials, reduction potentials of different reactions and different materials, and you can make a more powerful battery. You can maybe power your LED with less than 6 potatoes like I did in this video. I hope you guys enjoyed that. Thank you very much for watching. Let me know if you want to see something similar to this in a future video. I will see you guys in the next one.